Russia has just unveiled a new type of nuclear fuel that could change everything we thought we knew about reactors. It's called the OS-5 fuel assembly, and it carries inside it a secret layer of liquid metal that promises to push fast reactors into an entirely new league. If successful, this design could mean longer fuel cycles, less radioactive waste, and a real leap toward the dream of a closed nuclear fuel cycle. For decades, nuclear power has been stuck in a paradox. On one hand, it produces huge amounts of electricity with almost zero carbon emissions. On the other, it generates long-lived nuclear waste, struggles with fuel efficiency, and faces safety challenges that make many countries nervous. Traditional reactors, called light water reactors, run on uranium oxide fuel and can only extract a fraction of the energy stored in uranium before the fuel has to be removed. The rest, still full of valuable material, becomes waste locked away for millennia. But here's the catch. There's another type of reactor technology, one that has always promised to do better: the fast neutron reactor. Instead of slowing neutrons down with water, fast reactors let them keep their high energy. That allows them to burn fuel more completely, including materials that light water reactors leave behind as waste. For decades, scientists have imagined fast reactors as the cornerstone of a closed fuel cycle, a system where spent fuel isn't thrown away but recycled again and again until almost every bit of energy is used. While the concept sounds perfect on paper, the reality has been much harder. Designing fuels that can survive the harsh environment inside a fast reactor has been one of the biggest challenges. The temperatures are extreme, radiation damage is relentless, and the mechanical stresses can break apart ordinary fuel rods long before they've given up their energy. That's why most fast reactor projects have struggled to deliver on their promise. And this is where Russia's latest move comes in. The OS-5 fuel assembly is Rosatom's answer to that challenge. Manufactured at the Siberian chemical plant in Seversk in the Tomsk region, this design takes mixed uranium-plutonium nitride fuel, already a high-performance material, and adds a twist, a liquid metal sublayer between the fuel pellet and its protective cladding tube. At first glance, that might not sound dramatic, but what happens next is what shocked even seasoned nuclear scientists. The liquid metal layer changes how the fuel behaves under heat. Normally, as the uranium-plutonium pellet heats up, it expands. That expansion can press hard against the metal cladding, the tube that seals the radioactive fuel inside. Too much pressure and the cladding can crack, releasing fission products into the coolant. It's one of the limiting factors for how far fuel can be pushed before it has to be removed. The OS-5's liquid metal layer acts like a shock absorber. It improves heat transfer, lowering the fuel's operating temperature while coolant parameters stay the same. It cushions the cladding from excessive stress, reducing the risk of failure. And by keeping everything more stable, it opens the door to higher burnup, the measure of how much energy is extracted from the fuel before it's retired. Right now, Rosatom's early mixed nitride fuel for the Brest OD 300 fast reactor has been certified for burnup of around 6% of heavy atoms. That's already decent, but Rosatom's goal is to double it to about 12%. If they can achieve that, it means fuel stays in the reactor longer. Reactors need fewer shutdowns for refueling, and the amount of waste per unit of energy goes down significantly. Let's rewind for a moment. Nuclear fuel has traditionally been made of uranium oxide pellets stacked inside metal cladding tubes. This design has been reliable, but it leaves a lot of fuel unused, and the oxide pellets don't conduct heat very well, leading to high centerline temperatures and extra stress on the cladding. Nitride fuels, by contrast, have higher density and much better thermal conductivity. That means they can pack more fissile material into a smaller volume and keep cooler under operation, perfect for fast reactors. But there was still a problem. Even nitride fuel expands under heat, and in the brutal conditions of a fast reactor, that mechanical stress can't be ignored. The OS-5's innovation is to manage that expansion by literally adding a thin liquid metal bond around the fuel. The exact composition of the metal isn't publicly detailed, but the principle is simple. Instead of hard contact between pellet and cladding, the liquid layer fills the gap, transferring heat efficiently but flexing with the pellet's expansion. It's a deceptively simple idea, but it could have huge consequences. Lowering fuel temperature improves safety margins, Reducing cladding stress improves reliability, and pushing burn up higher improves economics and waste performance. For a country betting big on fast reactors, those are critical gains. So, where will this fuel be used? The answer starts with the Brest OD 300, a 300 megawatt electric demonstration reactor under construction in Seversk. It's cooled not by water or sodium, but by lead, making it one of the first lead cooled fast reactors to reach this stage. The Brest plant isn't just a reactor, it's the centerpiece of the ProRev or Breakthrough project. Around it, Russia is building an entire complex with facilities to fabricate new fuel, recycle used fuel, and refabricate it into new assemblies. The goal is a closed cycle where plutonium and minor actinides are recycled endlessly, reducing final waste and making uranium resources stretch almost indefinitely. Before OS5 can fuel the Brest reactor, it has to prove itself. The plan is to test it first in the BN600 reactor at Beloyarsk, one of the world's longest running sodium cooled fast reactors. BN600 has been a workhorse since the 1980s and it's still in operation today. It has already hosted many fuel experiments, including early nitride and MOX fuels. It's the perfect place to test whether OS5 really delivers on its promises. If it works, the next step is clear. Scale up from the 300 megawatt electric Brest to a commercial 1200 megawatt electric version known as BN 1200M. That's where the big payoff lies. A large fast reactor running on high burn-up nitride fuel could become the template for Russia's next generation of nuclear power plants. And here's where strategy meets technology. By pushing ahead with fast reactors and closed fuel cycles, Russia aims to stay far ahead in nuclear know-how. While much of the world is focused on light water reactors and renewables, Rosatom is betting on a future where uranium resources are fully used and nuclear waste is drastically cut down. If successful, they won't just be selling power plants, they'll be selling entire fuel cycle solutions, from enrichment centrifuges to reprocessing plants to advanced fuels like OS5. The hidden truth is, this gives Russia leverage. Countries buying into their systems could become dependent not just on Russian reactors but on Russian controlled fuel cycles. It's both a technological and geopolitical play. Of course, challenges remain. Regulatory approval from Rostekhnadzor is still pending. The performance of the liquid metal sublayer under long irradiation campaigns needs to be proven. Questions about cost, scalability, and safety will have to be answered before OS5 can move beyond test assemblies, and critics will point out that Russia's track record with some advanced nuclear projects has been uneven, but you can't ignore the direction of travel. With BN600 as the test bed, BRESTOD 300 as the demo, and BN 1200M as the ultimate prize, Rosatom is methodically moving toward a closed cycle that has eluded others for decades. If OS5 fuel works as promised, it could be the missing piece of the puzzle. Imagine if fast reactors really do become mainstream. The whole economics of nuclear change, uranium demand shifts, waste storage debates ease, and nuclear once again positions itself as the backbone of carbon-free baseload power. Looking back, nuclear power story has been one of potential, constantly undermined by problems, waste, fuel efficiency, safety fears, but breakthroughs like OS5 show that solutions are still being invented, new fuels, new coolants, new cycles, each one chipping away at the roadblocks that have held nuclear back. What shocked even seasoned scientists is not just the concept, but the timing. In 2025, while much of the world debates renewables, Rosatom is building and testing hardware that could rewrite the rules. Don't forget to like, subscribe, and comment your thoughts below, because the story of nuclear energy is far from over. And on Dezen, we'll keep bringing you the breakthroughs, the hidden truths, and the technologies that could shape our future.